We continue the introduction to differential equations, and next we'll talk about initial value problems. So here's the first definition. We call a differential equation with an additional condition in the form a function at some value is given, and such differential equation is called an initial value problem. Or we abbreviate it as IVP. And it doesn't matter what A and B are. In general, f of A is equal to B, but when A is equal to 0, then we can refer to, this is kind of what gives the name to this type of problems. When x is equal to 0, it's like the initial value. So if you know the output of the function at initially, then you should be able to figure out the function. So this is, again, what we call the initial value problem, and this is what we refer to as the initial condition. And here's an example. If you take a very simple differential equation, it is just that. It is a differential equation, and you may even know its solution. So y equals x squared plus c, and we refer to this as the general solution of the equation. But if you take the same equation and you add an additional condition, such as, let's say, y of 1 is equal to 7, then this now becomes the initial value problem. And what do we do with the initial value problems? We solve them. However, how do we solve them? We always start off by considering the general solution of the corresponding differential equation, and we take the initial condition and we interpret it as we should. That is, this, when x is equal to 1, y should be equal to 7. So that means if we replace x with 1, then y must be equal to 7. But when you do that, this creates an equation in terms of this unknown constant, in terms of the constant c, which now becomes a parameter. So we can solve for c, and we can learn that this is only possible when c is equal to 6. So the final conclusion is that y is equal to x squared plus 6 is a particular solution that satisfies the initial condition, and therefore this is a solution of this initial value problem. So once again, when we solve the initial value problem, we shouldn't have any parameters or constants. We should be able to find a particular solution. So let's try this example. Solve the initial value problem, which is this equation, and this is the initial condition, and we assume that we know the general solution for this differential equation. It is c e to the power 3x. So, how do we solve this initial value problem? Once again, we start with the general solution of the corresponding differential equation. How we got it, here it was given to us. In general, we would have to solve the differential equation first, and now we take this initial condition and we plug in 0 for x and 4 for y, and as a result we get an equation in terms of c, and c is equal to 6, and therefore y equals 6 e to the power 3x minus 2x minus 2 is a particular solution that solves this initial value problem. So let's try another example. This time the general solution will not be given, so we will have to figure it out first. And again, first we're going to find the general solution. And to find the general solution, we're going to interpret this question as the question about the antiderivative. So we find y, the unknown function, by finding indefinite integral of 3x squared minus 4x plus 3 minus 6 e to the x. And we just integrate this, so x cubed minus 2x squared plus 3x minus 6 e to the x plus c. So this is our general solution. And now we find the particular solution by taking the initial condition and plugging it in to the general solution. So y would be equal to 8, and for x we plug in 0. And c, it appears c is equal to 14. So the solution that we're looking for is y equals x cubed minus 2x squared plus 3x minus 6e to the x plus 14. So we solve this initial value problem. So in general, when we solve a differential equation, we should be able to answer two questions. One is how to find the general solution, and the other question is how to find a particular solution when some condition is given. So right now we discussed how to find a particular solution when a general solution is provided. So we definitely know how to do that now. So what we're going to focus on in the future is on how to get a general solution for any differential equation. And then we already know how to find a particular solution. So let's try to summarize what we already know. And as of right now, the only type of differential equation that we do know how to solve is a very simple one in the form y equals f, y prime is equal to f of x. So the general solution for this differential equation can be described in the form of an indefinite integral. So the unknown function y can be found by taking the indefinite integral of the function f of x. Here's an example. Let's solve this differential equation. So y prime is equal to 3x squared minus 4x plus 3 minus 6 e to the x. We have seen this before, so y we found previously as this integral. So again, there's nothing new here. What's interesting is that we also know how to find a particular solution in general when some initial condition is given. So if in addition to the differential equation, we also have some initial condition, then we can find the particular solution. So again, this was the general solution. And as I said previously, we can just, for any problem, we can just follow the same steps to obtain the particular solution. However, for something simple like this, we can express the particular solution in general. It may not be possible, but for this type of equations it is. We can express the particular solution in this form. So y would be equal to the integral and it may not seem trivial, but if you try to apply this formula on this example, once again, or rather this example, then what do we see here? According to this formula, y will be equal to the integral from x0, which is 0, to x, which is just a variable, and now we plug in f of t, so we replace x with t, dt, and we're going to add y of 0 at the end, according to this formula, right? And then what do we see? We have t cubed minus 2t squared plus 3t minus 6e to the t. Here we evaluated between 0 and x and add 8. And finally, what we get, plugging in x for t, we have x cubed minus 2x squared plus 3x minus 6e to the x minus, and then we evaluate it all at 0. So we get 0 here, here, and here. And when you plug in 0 for t in this expression, we get negative 6. And then we still have this plus 8. So adding negative 6, subtracting negative 6 and adding 8 will give us plus 14. So notice how we obtained the same exact answer here using the formula rather than this method. So again, this is the answer I'm pointing at. However, while it is possible for this particular type of differential equation, it may not be always possible to express a particular solution as a formula. So, so keep that in mind. So let's do one last example here. Let's solve this initial value problem in two different ways. One using the formula. So y is equal to the integral from x0 to x of 2t dt plus 7. So what do we get? T squared from 1 to x plus 7. So x squared minus 1 plus 7, which is x squared plus 6. Or alternatively, we can use the two-step process by finding the general solution and then finding the particular solution. So in step 1, we find the general solution by integrating 2x dx. And then in step 2, we use the initial value to solve for c. And c is equal to 6. So either way, we get the same exact answer. So this is an introduction to the initial value problems.